Now, in summary, what we have here is P, the list of all possible ways to construct any amount using only pennies, ones. N, given in this expression, is the list of all the ways to construct any amount using ones and fives. D, any amount using ones, fives, and tens. Q is again the list of ways to construct any amount using ones, fives, tens, 25s, and H also includes 50s. Now H, the most general term here, it will include terms like these, for instance, 1 to power 2, 5 to power 3, and 10. Because those cross terms will come from the products of each of these lists. Okay, so 1 to power 2 times 5 to power 3 times 10 means actually 1, 1, 5, 5, 5, 10, which is in fact one of the ways that we can obtain 27. Okay, so for instance, if you like 1 to power 3, 5 to power 2, 25 to power 2 is one of the ways we can construct. This is 50, this is 10, and this is 3. You get 63. This is just one way to obtain 63 cents. Okay, so how is this going to help me? Remember the question, what am I trying to find is the number of ways to construct 50. But these lists, they have the ways for every amount, not only 50. So for this to help me, what I'm going to do is a neat trick. And I'm going to replace this 1 with the variable x. Replace this 5 with x to the power 5. Replace this 10 with x to the power 10. 25 with x to 25. And finally, 50 with x to the power 50. Now, if I do that, these will become polynomials, right? They are going to become polynomials. Well, they will have infinite degrees, but that's no problem for us. But an expression like this is going to become x to the power 3, x to the 5 to power 2, x to 25 to power 2. In total, this will be x to power 63. Okay? But consider another way. Let's say 1 to power 13 and 10 to power, let's say 5. This also gives me 63. Now, if you plug in x for this and x to 10 for this, this will still give you x to power 63. Or consider another alternative. Let's say you get 150, 50 to power 1, and then let's say 5 to 1 and 1 to 8. This is still 63. And again, if you plug in x to power 50 for this, x to 5 for this, and x to 1 for this, what you get is x to the power 63. So all combinations appear in H, right? And moreover, all different combinations occur only once. But if I replace this coin with x to 50, this coin 25 with x to power 25, this coin with x to power 10, etc. Consider 63. All combinations of 63 appear exactly once. So this one appears once, this one appears once, this one appears once, etc. So to count them in the final polynomial that will represent h, I will just have to look at the coefficient of x to the power 63, because that will precisely tell me how many combinations that make 63 cents in total, right? The coefficient of x to the power 63 is precisely that the number of ways I can obtain 63 using 1s, 5s, 10s, 25s, and 50s. Okay, so the total number of ways to construct 27 cents will simply be the coefficient of the term x to the power 27 in h. That goes for any amount, right? If you would like to find the number of ways to construct 50, you just look at the coefficient of the term x to the power 50 in h. So in essence, h here is our generating function, and the corresponding term, the coefficient of x to the power 50, is the 50th number in my sequence, which is the number of ways to construct the amounts 1, 2, 3, etc. Okay, so what I need is the coefficient of the term x to the power 50 in this expression. Okay, so what kind of an expression is that? If you exchange the coins with x to whatever the denomination is, well, this is h. This is what h becomes. This polynomial, well, it's the polynomial of infinite order, but essentially it can be represented by this product where you have the infinite sum of x to the power k's, and this is the infinite power of x to the power 5 k's. This is the sum of x to the power 10 k's, etc. Because these are the coefficients they are going to contribute to. So this will be the sequence 1, 1, 1, 1, etc. But for 5, for instance, it's just going to be 0, 0, 0, 0, 5, 0, 0, 0, 0, another one, 0, 0, 0, 0, another one, etc. And the contribution of 5s. And the contribution of 10s, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, etc. Okay, so this is the generating function of the sequence, which corresponds to the number of ways to construct any amount in the sequence, 1 to infinity, using 1s, 5s, 10s, 25s, and 50s. Now, of course, we are not going to really expand out this by hand. If you can do that, of course, we will just look at the coefficient of x to the power 50. But there are ways to obtain the coefficient of x to the power 50. But for this specific problem, it's not really very short and it's not really much instructive, so I didn't involve it here. It takes a lot of time, and if you're interested, you can actually look at the book Concrete Mathematics, and there's the explanation of how we can obtain that in a relatively smart way, let's say. It's not very beautiful, or it's not very straightforward, let me just say, but there is a way to obtain this in an analytical way. However, if you have a computer, or if you have internet, let's say, or if you have an algebraic program like MATLAB, or if you have internet, you can use Wolfram Alpha. You can just expand this expression we have seen here, this polynomial function, and well, obviously it cannot give you the entire list, but what I have done here is I limited it up to 50, because, well, for instance, these are the sums going all the way to infinities. But to construct 50, I don't need all the terms. I just need this all the way to 50, this one just to 10, because, well, I'm not going to ever need 11 nickels to construct 50. It's 10 at most. So with dimes, I need at most 5. With quarters, I need at most 2, and this at most 1. So I just truncated my function, so to speak. So this is the expression. I entered Wolfram Alpha, and it gave me the expression. Obviously, I don't need to do it by hand. And when you look at the coefficient of x to the power 50, you see that it is 50. So there are 50 ways to construct 50 cents using ones, fives, tens, 25s, and 50s. So this is one way to do this. It's not very elegant, let's say, because, well, this is not really an analytical way to do this, but this result shows something else to us. Now, look at the ways of the first five, because you see 1, that is x to power 0. So this means you can construct 0 in a single way. And x, this says you can construct 1 in a single way. That's obvious with pennies. 2, you can construct in a single way, 3 and 4. Now, when you exceed 4, up to this point, you get 2x to power 5, 2x to power 6, 2x to power 7, 2x to power 8, 2x to power 9. Again, the number of ways to construct 5, 6, 7, 8, 9 are equal to each other. Why? Because if the number exceeds, let's say, a multiple of 5, you have no choice but to add pennies. For instance, if there are n ways to construct 100, okay, the number of ways to construct 103 should be the same, because there is no way other than adding just 3 pennies, right? So these are in fives, have the same coefficients. You have 4x to 10, 4x to 11. Let me erase this here. 4x to 12, 4x to 13, 4x to 14. And then it changes again at 15, 6 up to 19. And then 9 for 20, 21 up to 24, and so on. You get the idea. If you look at, for instance, 100, 100 is here, 169, it goes up to this point, and then 101, 102, 103, 104, 105, up to this point, 105, they have the same values because it's just adding pennies, okay? So this was another observation they use in this solution in concrete mathematics textbook. But one of the methods you can use here with such a question is if you have a computer or a mathematical programming language like MATLAB or others, or you can access the internet and maybe use Wolfram Alpha or equivalent. You can expand this expression and just look at the coefficient, which will give you the answer.